Yes, the next talk will be by Juan Maldacena on massless QED 3 and Affiliation.
Okay, first, let me thank the organizers for inviting me to speak here. So, let me check. So the outline of this talk is first we'll have a very long motivation, then we'll talk a little bit about QED3 in a magnetic field and a bit on QCD3 in a magnetic field. So we're interested in studying the dynamics of massless fermions in background magnetic field, including the electromagnetic interactions among the fermions. This is a variant of problems you're probably very familiar with. And my personal motivation came from studying the standard model at very high magnetic fields, fields so high that we can neglect the mass of the fermion. This is what it means, B bigger than m squared. Now, we could naturally have such high magnetic fields if we had magnetically charged black holes that are small enough. With magnetic monopole charge, of course, we don't know whether those black holes exist or not. None have been observed. As a side remark, fields in magnetars have masses bigger than the electron mass squared, but they are not large enough that the effects we'll discuss will be relevant. So those fields have, the magnetic fields of those magnetars have bigger than the electron mass squared by maybe a couple of order of magnitudes. So we'll always be discussing low energies, where we are looking at the system at energies much lower than the natural energy scale of the magnetic field, which is square root of B. And for that reason, when we have charged fermions, only the lowest Landau level is relevant. So we'll have a transverse plane, the magnetic field, and we'll look only at the lowest Landau level. And a fact that is important, as you know very well, is that there is a large degeneracy in the lowest Landau level, which is proportional to the area. And for each of these orbitals, so for each of the states that we have in the lowest Landau level, we get a massless field along the z direction. Okay, so from one, let's imagine we have one massless charge field, then we'll get a bunch of, we get n massless fields along the direction of the B field. Roughly speaking, one massless field per flux quantum. So before we continue, let us make a connection to what Edward Witten talked about yesterday on wormholes, which is what at least personally introduced me to this problem. So Witten mentioned that he mentioned space wormholes, and he said that in classical general relativity, they are not traversable. And this statement is definitely true classically, but it's not true once quantum mechanic effects are included. So the question here is, how does quantum matter, or maybe ultra quantum matter, help to build wormholes? Now, in classical mechanics, the stress tensor is positive, or a certain component of the stress tensor, so the Lie-like component of the stress tensor, more precisely energy minus momentum, is positive. And that underlies the classical proof that Edward talked about. And in quantum mechanics, on the other hand, it can be negative, but not too negative. Okay? And that implies that we can have some traversable wormholes. So we can have wormhole configurations that roughly look like this. So we have flat space. So this is very similar to, well, almost this is identical to some of the pictures that Edward showed last time. So we can have space-times with these topologies, flat space far away, and then two mouths, and they're connected. And this is what Edward called space wormholes. In addition, we have a time direction, and so we have this as space, and then we have a time direction, and we have a time translation symmetry. Now, these are the wormholes you can build in this way. I'll discuss a little bit more later how we build them. The wormholes we can make this way are not the science fiction wormholes that you read in your science fiction books. So science fiction wormholes are wormholes that allow you to travel faster than the speed of light. So you enter one mouth, and then you come out immediately very far away. Okay? Those would violate causality. The wormholes we can make this way are not like that. So if you were to travel outside the wormhole and it would take you the wormhole mouths are separated by some distance d, it will take you some time d to travel between the two mouths in the outside space. But if you travel through the wormhole, as seen, then the time it would take you to emerge from the other mouth, as seen from an observer outside, will be bigger than d, okay? So it will be a slow detour rather than a shortcut. So these wormholes do not violate causality. So that's good and reassuring. It's not good for science fiction books, or at least you would need to modify the science fiction book. So something nice that happens with these wormholes is that for the person that goes through the wormhole, because it's falling in a gravitational field and so on, the actual time it takes you to go from one mouth to the other is actually very short, much shorter than the distance d, okay? It's comparable to the size of the wormhole mouth. So that's, maybe you have to modify your science fiction so you'll emerge very young on the other side. Also, I mean, you can get the same effect by accelerating very quickly, right? And then smaller amount of time would take. But you will have to spend a lot of fuel. So this actually is an ecological way to do it where you don't have to spend fuel. Gravity does the work for you. Okay, so now in order to have a controlled solution, we need matter with sufficiently large negative energy. And the negative energy has to be somehow localized in that region. And we can do that by considering geometry like this with a very large magnetic flux that goes through the wormhole. There is no net source of magnetic, there are no magnetic monopoles here. There is just magnetic flux that goes through those magnetic lines. And we can put that large magnetic flux. And if that magnetic flux is very large, then the fermions give rise to Landau levels. And along each of those magnetic flux lines, there will be a massless 1+1 dimensional field. And that will be moving, most of them are moving along closed circles. And those closed circles then give some negative energy. And that negative energy will support that's the usual negative energy of massless field on a circle. And that negative energy will support your wormhole, okay? And if the magnetic field is sufficiently large, we have a large number of fermions, and then the whole thing will be a controlled solution. Okay? We'll be able to trust, we are able to trust all such approximations. And in fact, using this, you can find trustworthy solutions in the standard model. So where you would do this whole construction at very, very small distances, where you can approximate the fermions all as massless. So this will be wormholes much bigger than the electroweak scale. They exist as solutions of the standard model. They are not very useful for travel, okay? Okay, so that was motivation. I continue with the motivation. So this whole picture relied on this idea that you have this large degeneracy with precisely massless fermions. Now, we need to also include the interactions. And you can ask, what happens to all these independent massless fields when we include the interactions, the electromagnetic interactions, for example, or QCD interactions or whatever. And so what is the actual low energy description of the system? Now, it's been kind of argued, I maybe would say conjecture, that for QED4, in some old papers in the 90s, there is a mass gap for the fermions, that somehow these interactions lead to the fermions having a tiny little mass. So the mass is non-perturbatively small in the electric coupling. And for that reason, it's not very relevant if these wormholes I mentioned are very small, but they might be relevant for larger wormholes. And then the question is, what's the full low energy Lagrangian? And the idea is that the low energy Lagrangian is, well, the Lagrangian of electrodynamics. And then there is something you could call the chiral symmetry breaking, where you have a field A, an axion-like field, which you can view it as the bosonized fermions. And that starts out basically having a purely longitudinal kinetic term along the directions of the field. And then non-perturbatively gets a small transverse kinetic term, again, non-perturbatively small. This is a little more conjectural than the previous discussion. So we wanted to understand this better. And the way you argue for a picture like this is that the Coulomb exchange generates a 4-Fermi interaction between this effectively 1 + 1 dimensional massless fermions. And that interaction is marginally relevant, and it becomes strong at the scale M dynamical that I just mentioned before. And then you say, well, maybe it probably generates a mass cap. And this picture is also supported by a certain ladder approximation. So it's some summation of a subset of the Feynman diagrams that was done here. And so we wanted to understand this process a bit better. Now, you might also be interested in this problem because it has some similarities to interacting fermions or Fermi surfaces. They are also at each point on the Fermi surface, you have massless fermions. And this phenomenon of the boson getting some mass and so on has some flavor similar to the BCS superconductivity. And we thought that we could justify the results that people obtained before by using BCS-like logic, as explained by Shankar, where he explained that in the BCS theory is trustworthy because you have this effectively large N that comes from the volume of the Fermi surface, or the area of the Fermi surface, sorry. Now, perhaps one of you will tell me exactly how to do that, hopefully later. And as a further comment, there is also a connection between this problem and some problem in astrophysics, so the so-called relation to force-free electrodynamics. So this is what describes the theory I was discussing, so electrodynamics with massless fermions in some energy range, so some energy range which is the scale, it's bigger than the mass scale I mentioned, but below the magnetic field. And so it's a very simple theory where you take electrodynamics and then you impose as a constraint that E dot B is equal to 0. Okay, so you have Lagrange multiplier that imposes this. If you only had this, that would be a free theory. But once you impose this constraint, it's a non-free theory. But it's a theory that is classically well-defined. And it appears, astrophysicists study it a lot because it's a limit of magnetohydrodynamics in the case that the magnetic energy dominates over the matter density. Then the matter density, all it does is it imposes that there are no the currents along the magnetic field cancel any possible electric field that you have, and then you impose this constraint. And this is all 4 dimensions. This is a very long motivation. I'm still in the motivation part. Okay, sorry about that. And this is somewhat similar to the theory that Damson has been considering for the Fermi surface, in the sense that it's a bosonic theory that describes the excitations of the Fermi surface. Okay, that's all in terms of motivation. And so we wanted to understand this better, and we wanted to understand how to go from the UV theory, completely well-defined electrodynamics, to the infrared and compute everything there. And we haven't done that, sorry. But so what we did was we considered a simpler problem, something that turned out to be a simpler problem, which is to go to 2 + 1 dimensions. And that brings us to the subject of this talk, which is based on a paper we wrote with Thomas Dumitrescu. And there was also a paper by more Karin condensed matter physicists that appear in this case. And the problem was also previously considered by these authors. So the theory we're going to consider now is in 3 dimensions. So it's electrodynamics in 3 dimensions. We'll have 2 component fermions, and we have 2 flavors of each of these 2 component fermions. And 2 is the smallest number so that the theory can be made time reversal invariant. And depending on the regularization you choose, you might need to put a Bayer Chern-Simons term. And we choose the Bayer Chern-Simons term to be 1 to make sure that we have a time reversal invariant symmetry. So the theory has an SU2 global symmetry and also magnetic U1 global symmetry. So we first consider the case that the magnetic field is much bigger than the electric charge square. So electric charge square in 2 + 1 dimensions has dimensions of energy. So this is an energy scale. So in the absence of the magnetic field, this is the energy scale where the theory becomes strongly coupled. So we are at very high magnetic fields. So in this case, the theory will be weakly coupled. And okay. So we are interested in those very small energy scales, and we want to derive the low energy physics without any uncontrolled approximations. And it will be a relatively simple phase with a very simple ground state. And so perhaps what we wanted to understand was to calculate the low energy properties from the UV theory, the parameters of that very simple state. Now, as a first approximation, if we consider energies that are in between these two, the magnetic field, we have a large degeneracy, the Landau levels that we have discussed. And as you know very well, we have one complex 0 + 1 dimensional fermion or a fermionic oscillator per index I, per flavor. And so we have a total of 2 fermionic oscillators per orbital. So at each orbital, we have 2 possible states. We can have the unoccupied state. We can have one of the 2 fermion flavors, or we can have both fermion flavors. They all have the same energy at this stage. Okay? There are n, so they all have 0 energy at the stage we're talking about. There are n orbitals, so we have this structure for each of the orbitals. And the Gauss law for electrodynamics imposes, together with that Chern-Simons coupling, imposes that the average occupation number should be 1. Okay, so should be just 1 fermion in average. Now, in order to set up the computation, we first integrate out all the modes for energies bigger than some cutoff that we choose in between these 2 scales. So at this scale, the theory is weakly coupled, and we can do this, integrating out. And we integrate out all the higher Landau levels as well as photons with higher energies. And that leaves out the lowest Landau level and the low energy photons and integrated in the low energy effective theory. Yes, please. If that makes you uncomfortable, let's say the Chern-Simons level is 0. The point is that the value of the Chern-Simons level depends on exactly how you regularize the UV theory. So we've chosen to regularize it in such a way that the parity invariant theory has Chern-Simons level 1. Okay, so we are considering just what one would call the standard electrodynamics without the physical, let's say, Chern-Simons term. Okay. Is that more clear? Yeah. Yeah. So that's why I insisted it was the time reversal invariant theory. So, for example, if we treated asymmetrically the 2 flavors in our regularization, we could choose it to be 0. And then we would say we have 0 occupation number. So that would be another way to do this. But we wouldn't have the manifest SU2 symmetry. And we wanted to have the manifest SU2 symmetry. The final theory will be SU2 invariant, however you do it. So then the Coulomb interaction is some effective interaction, which is just the usual current-current interaction you're familiar with. So here are the ones that we integrated out. And we can find at this stage the lowest energy state, but demanding that each of these, so notice that this interaction is the sum of positive terms. So for each k, we have an operator and the dagger of that operator. So it's all positive terms. So we can try to find the lowest energy state, demanding that all these operators vanish when they are acting on the state. Okay. Now, this is an equation that we cannot impose in relativistic theory. So it's a well-known theorem that no local operator can annihilate the vacuum. But in this non-relativistic context, we can do that. I mean, non-relativistic in the sense that the magnetic field breaks the boost symmetry. So there is a very simple candidate 0 energy state, one candidate state, let's say one trial state, which is that we occupy just the fermions as one particular flavor running over all the orbitals. And then all other, and that's a 0 energy state that obeys the condition we said before. And so the SU2 symmetry is spontaneously broken. So this is essentially the same as a Heisenberg ferromagnet. And some of you might also recognize this as a version of the quantum Hall ferromagnet, which is the quantum Hall effect for fermions where we can neglect the magnetic dipole moment so that we have a global SU2 symmetry. And this problem was discussed by these authors in the 90s. Now, a small difference is that in these papers, the Coulomb interaction was in 3+1 dimensions, and this makes some small difference in what I'm going to say, not for what I've said so far, but what I'm going to say in a moment. It's also possible to find the simplest excitations, which are a fermion Hall pair. So we create a fermion of type 2, and we annihilate one of type 1. That creates a fermion Hall pair. And it decreases the value of J3 by 1 unit, the third component of the spin. This is the only state. These are the only states that have this value of J3. So we can take a combination that has physical fixed momentum. They correspond for large momentum to two particles at some distance. And you can find exactly the dispersion relation. Okay. And at small p, you find the quadratic dispersion relation characteristic of, as expected for Goldstone bosons. With a coefficient you can calculate precisely from the UV theory. So in this case, this you could do in principle for any potential, but in our case, it's just the Coulomb potential. And something important here is that the dispersion relation coefficient comes from momenta, which are at the maximum momentum, so at the momentum of order the square root of b, or the inverse of the magnetic length, the size of the wave packets of each orbital. So this low energy dispersion relation is telling us that we have Goldstone bosons associated with the SU2 symmetry breaking. We have only one because we have non-relativistic Lagrangian, which is first order in time. So at this level, we have this low energy Lagrangian that I'm sure is familiar to all of you, where we have a first order term in time with a coefficient that is basically fixed by that degeneracy of the Landau levels. And then a term that has to do with the gradient energy. So the target space is a sphere, and the coefficient can be computed once we know the dispersion relation, which we showed in the previous transparency. Now, this is not the whole story because we also have the massless photon. And you can ask how the photon couples. Naively, it doesn't couple to these Goldstone bosons because they are electrically neutral. They were made out of a fermion antifermion pair. But it could couple to the topological current of this sigma model. And you can understand that by noticing that we had this coupling here. And if we were to add a little bit of gauge field and a little bit extra magnetic flux, then there would have to be an extra coupling here of the extra magnetic field to this term, which was the kinetic term for the particles. And if you integrate this by parts, you get d of this A. So this A is some, let's say, one form such that the F field strength of that one form is just the volume form on the S2. So this expression. So that gives us a coupling, and you can call this is ordinarily called the topological current of the sigma model. And we can further dualize the photon into scalar by this transformation. So this takes into account this form of the dualization takes into account that coupling to the current I just mentioned. And then you end up with the final form of the Lagrangian for the low energy theory with all the coefficients fixed. So this Lagrangian has parts which have first order in time and second order in space for some of the degrees of freedom. And for some other degrees of freedom, you have second order in all 3 dimensions. So we have some modes that have linear dispersion relation, which is the photon, and then some modes that have quadratic, which have to do with the degrees of freedom of this sigma model. Now, the full sigma model has a target space which has the topology of a squash 3-sphere. So that's not a round 3-sphere, but some directions have been geometrically shrunk. And the symmetry breaking pattern is SU2 times U1 magnetic gets broken to U1, and this U1 is a linear combination of a U1 in SU2 and a U1 in the U1 magnetic. And these modes are the Goldstone bosons of that breaking. Now we can go back to the dispersion relation and consider not just the low momentum particles, but also large momentum particles. And you get this, of course, the simple picture of the two particles separated by some distance, and you have the electric flux going between the two. And in particular, the mass of a single fermion, so you try to separate it infinitely, is infinite. It diverges logarithmically. And that's one difference with the quantum Hall ferromagnet. There, the mass of the fermion was finite. Also, in that case, there were skyrmions, which were configurations that were wrapping the target space S2. And you could neglect the coupling to electromagnetism in some limit. Here, we have, instead of this S2, we have an S3, which has no obvious two cycles and no skyrmions. OK, so now we quickly mention the case of a small magnetic field. So we were so far considering this situation, very big magnetic field. Now we could consider very small magnetic fields. So in this case, we first set B equal to 0 and consider the strongly coupled QED3 theory. And it's debated what the low energy theory of that theory is. Some people say it's a CFT, some people say it's a sigma model. Here, we will assume the conjecture that we get a relativistic sigma model on a squash 3 sphere, which was discussed previously in this paper. By adding the magnetic field, one simply adds some charge under the U1 magnetic, which is one of the symmetries, translation symmetries in this S3. And then it turns out that if you do now the analysis here, the very low energy theory at scales much more than B becomes very similar to a sigma model we just discussed. And so it's natural to consider, to think that as we vary B from this situation to this situation, the IR phase is always smoothly connected. OK, so a slight generalization of this is to add more flavors. We have a similar story. Won't discuss it in detail. And finally, let us discuss the case of QCD3 in an external background magnetic field. And the magnetic field is a magnetic field for the global U1 baryon number symmetry, or the number of quark number current. Now here we have a very similar story after changing what needs to be changed. So let's consider the theory again with two flavors, with time reversal invariant symmetry. So we adjust the Chern-Simons coupling so that we have the time reversal invariant theory. And so now we have a fermion that for each orbital, we have the flavor fermion, but now in addition, we have a color index. So that's a difference from what we discussed previously. And another difference is that now instead of the Coulomb interaction, we have the color exchange Coulomb interaction, which is basically has at weak coupling. So when G is small, we have this very simple form for the interaction involving the color current. So there are A runs from 1 to the size of the color group of size of SUN, SUNC. And again, this Hamiltonian has the simple, the same property that it's the sum of positive terms. So we could try to find the vacuum such that the current annihilates the vacuum. And if we choose this vacuum, so this is an equation which we couldn't have as I mentioned before, in a relativistic theory, but we can have in this situation. And one candidate vacuum that obeys this is one where we take, for each orbital, we take the vacuum, and then we act with a color neutral combination of fermions. So we act with the fermions of all the various colors. We put an epsilon tensor, so this whole thing is color neutral. So this contains the NC fermions. And if we do this for all orbitals, then this state will obey this condition. And once you obey this condition, you can show that the dynamics of the gluons essentially decouples. It is not solvable at low energies, but it will be essentially the same as what you have for a pure gluon theory, which is you expect to confine, so it should be a confining theory. So we have the usual confinement of the three-dimensional pure glue theory. And we still get a calculable dispersion relations for these Goldstone bosons of the symmetry breaking. I didn't mention that, but maybe I should have emphasized that. Let me go back. Notice that when we did this, we picked one of the flavors. So flavor number 1, as we had done for electrodynamics. So this state also breaks the SU2 symmetry as before. And we expect to have those Goldstone bosons. Again, we have a calculable dispersion relation with a precise coefficient here. And at higher momenta, when so at low momenta, the fermion and antifermion pair are very close to each other. So they have low energy. But at high momenta, they are very separated. And in the electrodynamics case, we have the usual electric field between them. And here we'll have a color electric flux. Again, the same flux that we have in the pure glue theory. And so that's the picture at higher energies. So in conclusions, we discussed some aspects of QED3 in a magnetic field in the regime that E squared is much less than B. And we could solve the problem in a controlled way. We get a simple symmetry breaking phase and compute the parameters of the low energy Lagrangian. It's a very simple state. It's a product state. It's no entanglement. So in some sense, it's not ultra quantum matter, but the idea is that you can understand how this Archie flow works out clearly. And the dispersion relation of the simplest excitations can be computed even away from the low energy limit. And finally, similar ideas work for the QCD3 case. And in the future, we will also like to solve the 3+1 dimensional case, which I think is more interesting, and including both for QED and QCD. OK, thank you.
Yeah. Two very small questions. So about the non-abelian case, since the gluons decouple, do you get an S2 rather than an S3?
Yes, and that's a different. Yeah, that aspect is different. Yes.
And about the abelian case, an important fact about this S3 nonlinear sigma model that at least I found some time ago was that there is with collaborators that there is a pi. There is no skyrmions, but there is a half term that you must add to the action with angle pi. Yeah. You didn't mention that.
I didn't mention. We mentioned it in the paper, but we didn't. I went over this.
That is where the non-relativistic kinetic term comes from?
Well, the idea is that you need it for matching some anomalies. But yeah, we didn't explain where it came from. Yeah.
Just a very small question. When you wrote down the Hamiltonian, you had just the charge interaction.
Yes.
What happens to the current part? Or am I missing something trivial?
Yeah. So that comes from the fact that these fermions are localized. They are moving essentially only in time. They are not moving in space. So for that reason, they only couple to the charge. So
Current matrix element is 0.
yes, it's to the first order, it will be 0. That's right. So when we remember we put the cutoff at some scale that was lower than the magnetic field. At this stage, we have fermions that just move along the time direction. So in that approximation, they are not moving at all in the space direction. Once we consider by integrating out all the other fields, we still get some current, right? It's of higher order, and you can see that in order to reproduce the results, so that sigma model that I discussed in the infrared contains also spatial currents. So those will be generated by order terms in the interactions. I pulled a slightly fast one on you, so maybe since this point arose, I'll. So here we went from a term that contained a derivative with respect to t, right? That's we were discussing the coupling of electromagnetism, right? And at some point I wrote this as d as opposed to just dt with all the derivatives. So the other terms, are necessary for gauge invariance and should come from higher order terms in that effective Lagrangian that were not necessary for discussing this. And we have a longer discussion of these other terms in the paper if you're interested. Yeah.
slide, you hit this S3 target space.
Yeah.
Are there instantons wrapping this S3 and what are the consequences? And related to that, there might be a theta term that you can add. So what's the UV precursor of that theta term?
Well, the theta term is what Sohar asked about. It's there with a pi coefficient.
What you said, Hopf term?
No, I didn't, I misspoke. There is a theta term that's associated to pi 3 of S3. We stated it was pi that must.
Okay, so that's not the Hopf term.
Yes.
And what's can you change its coefficient by changing the UV theory?
Well, the coefficient is set by, well, you cannot change the coefficient continuously because we assume we had time reversal symmetry. So coefficient is either 0 or pi.
What term should you add to turn on this term? Okay, let me ask it differently. For theta equals pi, some units, it should be also time reversal of the guy.
Yes, the theta is pi, and you need the theta equal to pi for anomaly considerations. Yeah. Yes, there is a term I didn't write. Implicitly, I omitted this term. Sorry. It is in the paper. I just tried to oversimplify, perhaps, in my presentation.
Question about the absence of skyrmions. So the physical picture is it that skyrmions can engage charge, and so they are not there in infinite energy, and they're out of the spectrum.
Yeah, the idea in the electric picture is that there is some energy of the skyrmion that comes from the elastic, let's say, energy of this sigma model, right? And then in the 3+1 dimensional case, well, in both cases, there is also some electric energy, right? Because they are charged, they carry electric charge. And in 3+1 dimensions, if you make the skyrmion large enough, that second term is subleading compared to this elastic energy term, right? So you can ignore it, or you can think of it as particles which have a little bit of charge. In this 2+1 dimensional case, the two terms are of the same order. So you can't say, I first solve the equations for the sigma model, and then I include the charge later. You have to do them at the same time, and when you do that, you find that you can't do it. There is no topologically.
Yes, I have a very basic, kind of almost embarrassing question. So you have a background magnetic field. On top of that, you have gauge fluctuations.
Yes.
So what is it, something by UV, some cutoff that prevents you from shifting away the background field? If you kind of think of it non-perturbatively, where you integrate all the gauge fields?
So well, maybe. So we have this background field. So the field is dynamical. So in this QED case, in the case of electrodynamics, this field is part of the dynamical fields of the background. And you can think of this as a configuration with a constant charge density. So this U1 magnetic symmetry. And so you can think of that as a theory that we consider it in a state that has a constant charge density. That's the magnetic flux. And we are expanding around that state. You could consider other states. So the theory contains other states. But if you start with this state, you will not go to the other states because this is a conserved charge. Because, yeah, it's a charge that is conserved. So.
Motivation, like, I mean, there's many different kind of aspects of this quantum Hall physics. But when you look at the 3+1, is this kind of symmetry breaking particularly important for example, forming wormhole, or is there some?
Well, there is a question of whether it's important for the wormhole I discussed. Probably not, or maybe the QCD part is important, where maybe if I take the formula that I mentioned for the mass of the fields, if you have electrically charged fields, if you consider just electrically charged fields, like the right-handed electron, for example, then that would not be very important for wormholes of most sizes. Might be important for relatively big ones, or magnetically charged black holes with relatively big sizes. But analyze in the right theory. So we are just considering this ideal as things for the time being. So this was just a motivation for introducing us to this problem, but then at least personally, I was interested in understanding this problem that looks like a very basic physics problem, and we like to understand it well and clearly. I guess that was the motivation. I think Thomas didn't have this motivation, just by the way, my collaborator. He just wants to understand this as a problem in quantum field theory.
Maybe last question, John.
Is there a physical realization of QCD in a baryon magnetic field?
Could you repeat?
Yeah, so the question is whether the physical realization of QCD in a baryon magnetic field. And well, of course, if you have real world QCD, so you have both there is some flavor. So the physical electric field is a combination of this baryon number electric field and some flavor electric field. And so you would have to consider both of them. Yeah, so but this is a simpler problem. That's why we discuss this first. But you can complicate it a little more and discuss then the other one. And of course, in the real world, we're interested in the 4-dimensional case of this. And so there's been some work, of course, to try to understand the 4-dimensional case. So in heavy ion collisions, for example, you have the protons moving very fast. And so you generate very high magnetic fields. And so people are interested in the physics of this for that reason. Yeah, that's another motivation I didn't discuss. But that was the main motivation for the older papers in the night.
Okay, great. Thank you, Juan.